So welcome. Today we're going to start looking at the first part of thermodynamics. There's 4 chapters in here. We're a little bit behind, so I'm going to go through quite quickly. There's a bit later on that I know that I can save time on. So we're going to talk about a few things today. We're going to talk about temperature and a thing called the zeroth law of thermodynamics. And then thermometers and temperature scales. We'll talk about thermal expansion, and we'll talk about the macroscopic model of a gas. So this is kind of like, this is before people really knew what was going on. This is like, you know, there's a thing called hot, a thing called cold. There's things expanding, things contracting. We have thermometers. We don't really know what they measure and that kind of stuff. We do now know what they measure, because now we have an atomistic view of how things behave. But originally they had no idea. They didn't sort out thermal stuff until the 1850s. And by then the Industrial Revolution was well on its way. We had steam engines and the like. But it was one of the last things in classical physics to be sorted out. It's very confusing until then. So let's talk about temperature and the zeroth law. Temperature is a direct measure of the average molecular kinetic energy. Well, you know, we know that now. They just knew that temperature was hot or cold. We now know it's basically in a solid, it's how much the molecules vibrate. Or in a liquid, it's how fast the molecules move. Or in a gas, how fast the molecules move between colliding with the walls of the container. So, you know, it's all about kinetic energy. We now know that temperature is a measure of the average kinetic energy per particle, but they didn't know that. So basically all they knew was we have this thing called hot and cold, and we can measure it in degrees. 2 objects that are in thermal equilibrium, if the heat energy is exchanged between them, despite the fact, if no heat energy is exchanged between them, despite the fact they're in thermal contact. So if I touch something and there's no insulation between us, so that I can feel the temperature difference, heat can flow into me or out of me, I'm in thermal contact. So if there's an insulator there, I'm not in thermal contact. But if there is no insulator there, so when I touch something, I can feel it's hot or it's cold, or even if it's the same temperature, if I could feel hot or cold, I'm in thermal contact. And if I touch something, I'm in thermal contact with it, and it is basically no heat flows from me to it or it to me, then we're in thermal equilibrium. Now what that means is we're at the same temperature. So we say the 2 objects are at the same temperature. So you're in thermal contact if heat can flow backwards or forwards. And you're in thermal equilibrium if no heat does flow, even though you are in thermal contact. And that occurs when you're at the same temperature. Heat flows because of differences in temperature. That's a bit unusual. 2 objects are in thermal contact with each other if heat energy can be exchanged between them. And then heat is the transfer of energy from one object to another object, and is a direct result of a difference in temperature between the 2. So what are we doing? We now know there's energy inside one object, there's energy inside the other object. If there is a difference in temperature, energy will flow from the hot object to the cold object until they have the same temperature. So there's a little bit of complication going on here. Heat is a name we give to thermal energy when it's been transferred. It's like salary or wage. When it's in your boss's bank account, it's called money. And when it's in your bank account, it's called money. But when they're handing you the check, they say, this is your salary. It's a special name you give to money when it's been transacted. Same thing with heat. When it's in the one object, it's either thermal or internal energy. When it's in the other object, it's either thermal or internal energy. But when it's been transferred, we call it heat. So recognize that's been transferred. Yes?
So, and it's always heat that flows into cold, right?
Heat always flows from hot into cold.
From hot to cold.
Yeah. Spontaneously. Okay, you can actually drive things backwards, but you've got to work really hard to do it. But spontaneously, if you just put these two things in thermal contact, the heat energy will flow from hot to cold, always. And, but heat is not a measure of the total amount of energy in an object. It's the amount of energy per particle. So you can end up with these ironic situations where you have a very hot small object and a very cold big object. An ice cube the size of this table and a spoonful of boiling water. The spoonful of boiling water is clearly hotter, but it contains less energy than the ice cube size of this table. Now that's not obvious until you really understand what's going on with the atoms. It wasn't obvious to the people 150 years ago, but to us now we can see that although the atoms of the ice don't have as much energy individually, because there's so many more of them, then they add up to having more. It's like us and Bill Gates. Well, not us, but the country and Bill Gates. You know, Bill Gates has more money per person than the average American does. He's an American, but I'm going to separate him for a minute. I mean, it's more money than per person. So he's wealthy, and the rest of us not so wealthy. But we have more money than him if we add all our money together. So it's like we're the ice cube. Individually, not so much, but there's a lot of us. He's like the spoonful of boiling water. Only one of them, but man, lot of energy for one person. It's like that. So we've got to be a little bit careful in how we interpret things. Okay, zeroth law. Whenever there's a zeroth law, what that means is they wrote the laws and then they realized they needed one that was more fundamental because people weren't getting the problems right. So they went back and did a zeroth law. Zeroth law states that two objects that have the same temperature, two objects have the same temperature if they're in thermal equilibrium. It's actually, if you read it, sometimes it's written very complicatedly, but that's what it means. If I have the same temperature as the cell phone, and the cell phone has the same temperature as the table, I have the same temperature as the table. It's as simple as that. Okay. Go. Let's talk about hot and cold. I want to be able to characterize it. I'm a scientist. I need to be able to figure out how hot is it, how cold is it. So I'll use anything which shows an effect that's reproducible based on temperature. So I will use the expansion of a thin column of mercury. That's what they used to use, a little tube filled with mercury. It would expand if it got hot. I will use the expansion of a little thin column of alcohol. I'll dye it red so I can see it, but you know, I'll use that. Hey, when I started working with electricity, I found that there was this thing called the thermocouple effect, where different metals, the junction between different metals at different temperatures would have a little voltage generated between them. That's a useful way of measuring temperature differences. I can use the resistivity of some materials changes significantly with temperature. That would be useful. I can do the fact that gases expand as you change their temperature. That's a way of measuring temperature. I can use the fact that little liquid crystals, like you have on your calculator and the like, liquid crystals, sometimes they change color depending upon the temperature. I can use the fact that things glow with different color depending upon their temperature. So I can actually not even touch something. I can look at the light glowing from something. Not talking about reflected light, talking about glowing light. And I can see a temperature measure from there. Anything that's reproducible, I will use to measure temperature, because it's really important. So a thermometer indicates the temperature by displaying some physical property that varies in temperature. And some physical properties include volume and length and pressure and resistivity. There's a whole bunch of things. If you have an outdoor thermometer, one of those little plastic ones you put on the wall, Often they have a bimetallic strip inside, just a strip made out of two different metals, and one expands more than the other, and it turns a needle. Anything that will indicate temperature in a reproducible way we're going to use. Okay? So we have a whole bunch of different ways of making thermometers, but what do we put on the scale? Well, it depends. First person to look at this that we care about is a guy called Fahrenheit. And Fahrenheit was actually interested in medicine, so he wanted the temperature of the human body to be about 100 degrees. So he put the thermometer under somebody's arm and let it get to the certain length and marked and said, that's 100. And then he got the coldest concoction he could make, and that was ice brine. That's basically ice in salt water. And he said, that's 0 degrees. And then he marked, you know, all the steps in between. Well, that's fine. Maybe I've got a fever when I'm doing my experiment, so my thermometer's not going to work as well because I'm going to be hotter than it should be. And maybe I don't make the ice brine so well because it's like a mixture of things. So it's not a very good scale in terms of reproducibility. It's great for him, but not a very good scale. So we'd prefer it if we had the temperature of steam coming off, of water going to steam. And we'd prefer it if we had the temperature of water melting from ice. So we call one a steam point, an ice point, or boiling point, an ice point. And what we find with the Fahrenheit scale, that this is 212 Fahrenheit, and this is 32 Fahrenheit. And okay, once you know that, you can calibrate all your thermometers all over the world in terms of the Fahrenheit scale, and it works. And so that was a decent temperature scale. It's good in some ways in that there's 180 different degrees between boiling point and freezing point, which is quite a fine scale. It's lousy in some ways. It works well for temperature differences. This is 20 degrees hotter than that is. That's great. It's awful in that 0 degrees Fahrenheit is not no temperature. It's not as cold as it can get. It's not the bottom of the scale. It's just a convenient thing that he could get to. Problem is, you can't in everyday life experience 0 degrees, meaning no temperature. So you're kind of stuck halfway up this temperature scale, but you don't know where the bottom is. This is a real problem. But for differences, it works great. So for day-to-day things, you know, how hot are you? Do you have a fever? It's brilliant. It works really well. And in the United States, we use it to this day. Maybe, I don't know, maybe 30 years later, 50 years later, along came Celsius. Celsius was one of these decimal people. He wanted everything to be a factor of 10 or 100. And he goes, this is a crazy scale. We're going to basically set up the steam point and the ice point. And we're going to call steam point 100 degrees C and ice point 0 degrees C. And there's 100 steps between the two. That's fine. It works for temperature differences just great. In Europe, they've used this scale for, I imagine, hundreds of years, actually, since it was invented. Britain used the Fahrenheit scale for the longest time, apart from in science lab. In science lab, you used the Celsius scale, but for the most part, you used the Fahrenheit scale. Weather was always in Fahrenheit. So, for instance, my generation is the changeover generation, and when I left the Britain, we were still talking about temperature for a day in degrees Fahrenheit, just like the United States. But within a few years of me leaving, the weather forecast started being done in degrees C. So my brother, I've noticed, just thinks in degrees C. He has to do the conversion. He says, it's a hot day, you know, it's, 20 degrees, 22 degrees C. And I'll go, what on earth is that? And he'll go, oh, it's so-and-so. Whereas for me, it's a hot day, it's 90 degrees F. What is that in degrees C? I got to think about that. We're about one of the few countries that still works in Fahrenheit for day-to-day colloquial language. You know, rest of the world has gone with Celsius. It makes it tough on our students learning science because they have one temperature that they see on television and there's another temperature they see in science class, which is an issue. It's not the end of the world, but it's an issue. Again, suffers from the fact that 0 degrees C is certainly not as cold as it gets. I mean, you know, if you live in the north, you know that you get days that are 0 degrees Fahrenheit, and that's a lot colder than 0 degrees C. So I remember moving from Florida to Boston in November. I've never been so cold in my life. I remember going into work one day and smiling, and my lip cracked and blood came down over my teeth. It gets really cold sometimes, and you realize that, you know, people move south to retire because they want to live longer. It's like, you know. So you can certainly get colder than 0 degrees C. And it would be nice if we had a temperature scale that actually began when it was the coldest temperature that there can be. And that is, so in about 1850, he wasn't Lord Kelvin at the time, but he became Lord Kelvin. A famous scientist wrote a letter to the Royal Society and said, listen, we got to find out what absolute zero is. Because if I take 10 degrees C and I double it to 20, I have not doubled my average energy per particle. I might have doubled the number, but I've not doubled my average energy per particle. So I've not doubled my amount. I've doubled the number, but not the amount. If I triple the degrees Fahrenheit, it doesn't mean anything. It's 3 times the number, but it doesn't mean anything. We need it to be that when I double my temperature, I double whatever temperature is. And temperature is the average kinetic energy per particle. So I need to find out what the temperature of no kinetic energy per particle is. And that's an issue, because you can't easily get there. But there's a trick. And the trick is, I cut it out. Okay. And the trick is, you basically say, look, when I have no kinetic energy per particle, my gas particles have no kinetic energy. So they're not moving. So they basically lie at the bottom of the container. So they don't exert any pressure. So if I take the melting point and I take the boiling point and I say, okay, for my trapped volume of gas, what pressure do I have? And for my trapped volume of gas, what pressure do I have? And I make that 0 and I plot my line down. That is absolute 0. Because there's no pressure. So there's no kinetic energy per particle. Now, is it linear? It's pretty linear, and you can check that in the bits that we can get to. You can actually change the temperature. It's pretty linear. So we can find that. Yes?
Sorry, so what's that A2 for?
AZ is absolute 0. Okay? And so we do that experiment, and I think you did that experiment in class, in lab?
Lab, yes.
In lab, and you found that that was minus 273 degrees Celsius.
Correct.
So Lord Kelvin said, let's call that 0, and let's start counting up from there. So he didn't change the size of the degree C, he just moved the 0 point. And so melting point is 273 Kelvin, and boiling point is 373 Kelvin. Now, notice something. 273, let's call that 300 Kelvin. 373, let's call that 400 Kelvin. A kilogram of ice at 0 degrees C has the same number of particles as a kilogram of water at 100 degrees C. Say, yeah, agreed? The average kinetic energy of a molecule of ice is 3/4 the average kinetic energy of a molecule of water that's about to boil. 3/4. So a kilogram of ice contains 3/4 the amount of energy as a kilogram of boiling water. That's like phenomenal. I mean, that's like, you think of ice as as needing energy. It contains 3/4 the amount of energy as boiling water. It's full of energy. It's just not as much as boiling water, and we're in the middle. Our temperature is in the middle. So when we touch boiling water, it burns us because the energy gets into us real quick. And when we touch ice, it burns us because the energy leaves us real quick. But it's not that ice is negative anything. It's 3/4 the amount of energy as boiling water. So this Kelvin scale and its ability to enable ratios. I can ratio volumes. I can say I double the volume, I triple the volume, and it means something. I can ratio pressures. I can say I triple the pressure, I quadruple the pressure, and it means something. But it's only when I use the Kelvin scale that I can triple the temperature or quadruple the temperature, and it means something. If I do that in the centigrade scale or the Fahrenheit scale, it doesn't really mean anything I can rely upon. It's hotter, but what does that mean? So this was a huge breakthrough, and it really enabled us to make a lot of strides. If in doubt, use Kelvin scale. If you're doing the differences, it's the same. 273 taken away from 373 is 100. 100 minus 0 is 100. When you subtract and add Kelvin, centigrade, it's all the same. When you subtract, maybe not when you add. When you do ratios, huge difference. If in doubt, unless you've got a good reason not, if you can't decide, my advice is you go with the Kelvin scale. It will be better. The Kelvin scale is needed because 0 degrees would mean 0 kinetic energy per particle. It was developed in about 1850s. If you want to go from Kelvin to degrees C, well, Kelvin equals degrees C plus 273. And if you want to go from if you want to get degrees Fahrenheit from degrees C, you have this equation. I don't learn equations I don't need. I basically look here and I do this. I'm sorry, it's a real small diagram. And basically what I do is I say, okay, this is 0 degrees, and that's 100, and this is 32, and this is 212, and I say this is, of course, Fahrenheit, and that's Celsius, and I say y equals mx plus b. So my y, well, my y is basically degrees Fahrenheit, and my x is degrees C, and my slope, it's rise over run, 180 over 100, and my y-axis intercept is 32. It's the same equation. So I don't learn that equation. I can figure that equation out anytime I want because I understand a straight line. Okay. How cold can we get if you make a really good refrigerator, which is probably the ones when I was a student, they'd make concrete structures that were about the volume of this entranceway, going, the depth of it and the width of it and the height of it. So what? Maybe 1 meter by 3 meters by maybe 4 meters, that concrete structure, because you don't want vibration, because vibration will transfer energy in, which raises the temperature. If you do that and you use a lot of liquid nitrogen to get you somewhat cold, 77 Kelvin, and then you put in liquid helium, and you pump on it and you do some tricks and you use various techniques, you can get down to milli-degrees, thousandth of a degree Kelvin. And we care about that because the physics of materials changes when you go to those really low temperatures. When you don't have these vibrational phonons going through because of the temperature effects, then things behave somewhat differently. There's an awful lot of revolutionary science comes out of low temperature stuff. Superconductivity came out of there, basically. My college roommate spent 2 years building, they call them refrigerators, building a refrigerator. He had the coldest place in the northern hemisphere inside his machine for about 3 months. And then somebody in France built one that could go even colder, so he lost the record, you know. He spent 2 years shoveling concrete. I felt so sorry for him. I thought, he's not doing any science. But, you know, in the end, he built this amazing instrument, and then he did science at the end, which was quite interesting. Now, I think last time I heard, he worked for on a radio telescope. So convert 1400 degrees C to degree Kelvin. So Kelvin is equal to degrees C plus 273. So Kelvin would equal 1673 Kelvin. Traditionally, we don't put down degrees Kelvin. We put down just K. Convert 66 degrees Celsius into Fahrenheit. So degree F is equal to 9/5 degrees C plus 32. So degree F is equal to 9/5 times 66 plus 32. And I have, where's my little handy dandy calculator? So I'm going to go 9 divided by 5, enter, times 66, enter, plus 32, enter. I'm getting 150.8. And then, which is the smaller unit? Degrees Fahrenheit, degrees C, or degrees Kelvin? What do you think? Going to be A. Remember, there was 212 down to 32. In the same range, we had 100 going down to 0. In the same range, we had 373 going down to 273. So this was 100 steps. That was 100 steps. And this was 180 steps. So the degree Fahrenheit is the smallest one. Okay, so we'll draw a line. So now we can measure temperature. Let's look at what happens when we change temperature. And the first thing you notice is that things expand. Solids expand, liquids expand. So the volume of a liquid will expand. The length of a rod will expand. The area of a plate will expand. The volume of a cube or a sphere will expand. For most things. Over at least some temperature, weird things happen when you get near the melting point. It's becoming, material properties are changing. But for the most part, there's at least a certain range of temperatures over which you can find a linear bit, where if I change the temperature, notice what I'm saying here, if I double the change in the temperature, I double the change in the length. Yeah. Yeah.
Is that formula right entirely?
No. That's not right. And now I'm going to have a problem here because I'm not even sure I can remember the formula for this.
We can do it.
Delta L.
Yeah, it's delta L equals,
Alpha L initial.
yeah,
Delta T.
times delta T. Yeah, thank you.
Why doesn't it have it?
It's just word. It's Bill Gates. He's got all that money, and I feel like going to him and saying, "Give me some." No, it's not him. It's just the way it is. So these notes are about 20 years. So these notes are about 20 years old, and they've been from Mac to PC, back to Mac, back to PC, and they lose things as you do it.
As old as some of us. As old as some of us.
Yeah, 19. Oh man, some of these are like really old actually. Yeah, some of these are really old.
You teaching us some old material?
Always. I reuse, recycle, and teach it. So what you see is these linear bits. Now, not every material behaves the same way. Some of them, they behave nice and linearly, but they change by a lot. And some of them, nice and linear, but they change by a little bit. So I need a figure of merit. I need to write down these empirical, that means experimental values. I don't get this by theory, I get this by experiment. And I put them in a book, and it's the engineer's handbook. And pretty well, if you look on engineers' shelves behind them, there'll be a CRC handbook. And it's basically got everything you can imagine is in there. They keep updating it because there's new materials. And so we need a figure of merit, and the figure of merit is this guy. What we say is a rod's length changes with temperature. Usually the rod gets longer as the temperature increases. The amount of expansion depends upon the material, the temperature change, and the original length of the rod. It's a little bit complicated. If you have a long rod, it expands more than if you have a little rod, because it's like there's more of it to expand. So we say we can define this thing called the coefficient of linear expansion, alpha. And yes,
What does the A stand for?
it's alpha.
No, I know, but what's it for?
It's the coefficient of linear expansion. Okay? So we can define this coefficient of linear expansion, alpha. This alpha value, so each one of these will have a different alpha value. Different material, different alpha value. It can also affect the volume and areas. So they have like a beta for the area and so on like that. And okay, so that's kind of interesting. We can look it up in a book. I just want to give you a little bit of just to show you that life is interesting. For water, the coefficient of expansion changes with temperature. And so what happens is that as you go colder and colder, water should get less and less volume, which means denser and denser. Yeah?
It's the opposite, right?
So what happens is when you get to about 4 degrees, that trend stops and it starts increasing its volume. Otherwise, when you had a pond, if the coldest water was on the bottom, the pond would freeze from the bottom. And if you imagine the first fish that nature ever produced swimming in this pond, and the first winter comes along, and it freezes from the bottom, and the fish goes on swimming, and then it freezes from the bottom, and the fish goes on swimming, and it squeezes from the bottom, and the fish goes on swimming, and then the whole thing freezes, and the fish lies on top and freezes to death. Well, that's not what happened. Because what happened was the coldest water, once it got below 4 degrees C, was on top, and it froze on top, and you got this nice insulating layer. The ice is a really good insulator. And so the fish swam happily at 4 degrees C, or thereabouts, for the rest of the winter, and, went on living. So fascinating behavior of water. Water is like, there should be a degree in water, because it's got so many properties that are just unexpected, that are just really useful properties.
I have a question. Okay, so you're talking about how this formula it gets longer, right?
Yeah.
Okay. So what about rubber? Because I know rubber shrinks.
Oh,
when it's-
yeah, so there are materials where it does not get longer, it gets shorter.
Okay.
They're exotic materials.
And
But
then that'd be like a negative number.
yes, that would be a negative number, provided that it was reliable. So do you happen to know if I change the temperature of like a rubber, is it repeatable, or does it damage the structure of the rubber? I think if you do it with moderately, it'll be repeatable, and so I suspect you can find it. You might want to, how many people here have a CRC handbook? Ooh, so go online. They might not do it anymore, actually, because it's all online, but in my day, CRC would basically give you this book, this huge book for like nothing, because it was like they produced thousands of them. It was advertising for a company. So check online and see if you can still get one, or at least look at the engineer's handbook and just know where it is and tag it on your computer so you can look stuff like this up, because it's fascinating to look at real-world numbers. As a physicist, I don't worry about these real-world numbers. They're all beneath me. I deal in up here. I'm up here, and everything I build falls down. Whereas as an engineer, you guys need to study it and make sure my house does not fall down. Because, yeah. So let's do one. Oh, we've got a couple of things, first of all, to talk. At room temperature, a brass ball will just fit through a hole in a brass plate. So here's a brass plate, and there's a hole in it. And then I take a brass ball, and this brass ball just fits through it. What will happen when only the ball is heated up to a significantly higher temperature? So I'm only going to heat up the ball. And brass behaves normally. It behaves where most things behave. So what will happen? The ball will easily fit through the hole, whereas before it only just fit through the hole. The ball will just fit through the hole, or the ball will no longer fit through the hole. What do you think? No longer. It expands, so it no longer fits through. What will happen when only the plate is heated up to a significantly higher temperature? So this is interesting.
Does it expand both ways?
So this is interesting. I want you to use your gut intuition, and I want you to answer that question. You can talk to your neighbor if you like. So what happens now? You're heating up both of them to the same extent, you know. So will the ball get bigger and the hole get smaller?
Just the plate.
Oh, this is just the plate. I'm sorry. So will the hole in the plate get bigger? Will the hole in the plate get smaller? What goes on? Very interesting question. What do you think? What do you think? I'm going to give you just a couple more minutes. I'll give it till the minute. This is worth a minute of our time. Yes, I think so. Can you get it as a book?
I have a Merck index from like 1975.
Oh yeah, okay, yeah. Yeah, CRC in Britain, I think, and Merck over here.
Okay.
Yeah. Okay. What do people say? I bet it's split. Yes, it's split. Yes, I bet it's split. And this is not obvious. The answer is that the ball will easily flit through the plate, which is A. But don't feel bad if you said C, because what happens is, the way you get this is, you say, there are only 6 atoms on the inside of the circle. So this is, please, there's only 6 atoms on the inside of the circle. And you've heated them up, so they occupy more space, so they move further away from each other. Things expand by moving further away from each other. So the hole, which was there, becomes a hole which is there.
It'll be a bigger hole.
So a bigger hole. And I would not have guessed that. I would have said the metal expands and squishes this hole up, and in fact it all gets bigger. It's amazing. So that would be easily fits through. And then what will happen when both the ball and the plate are heated up to the higher temperature? And the answer is it will just fit through the hole. They're both having the same effect. What's the coefficient of linear expansion of a rod that has a length of that and a... Okay, so I need to convert this into an image for me. So this is 30 centimeters. And that's 40 degrees C. And this is 50 centimeters. And this is 45 degrees C. So I said that delta L is equal to, what was it? L naught? Alpha. Delta T? Yeah. So let's have a look. What is the coefficient of linear expansion? Alpha is equal to delta L over L naught delta T. So alpha is equal to delta L. What's my change in length?
Doesn't matter.
20 centimeters.
I'm going to leave it in centimeters.
Alright, so it doesn't matter the unit.
We'll get to that. So I'm going to leave it in centimeters. So it's going to be 50 minus 30 over L naught. That was 30 times delta T was 5. Let's put it down as 5. So that's 20 over 150. So alpha equals 20 over 150. 20 divided by 150, and I'm getting 0.133 units. Look at your equation. Tell me what the units will be. Look at your equation. Look at your equation. And tell me what the units will be. Yep. It's going to be 1 over degree C. Yes.
So how do we know the initial length is? It's just going to be...
Because it says that has a length of 30 at 40 and 50 at 45. I'm going from there to there.
Okay.
On a test, I'd be more careful with my wording. But so the way you get your units is you look at your equation, and I said that was change of length is in meters, and my original length is in meters, or centimeters in this case, and they're going to cancel. And degree C is on the bottom, so 1 over degree C. And that's why, because the centimeters cancelled, that's why it doesn't matter if I'm in meters or centimeters in this case. If you think about it, I could have said 0.2 over 0.3 times 5, and I would have got the same answer. Yep. So it turns out it doesn't matter in this case. Again, I'd like you to go to, unless you have a good reason not to go to standard SI units, but occasionally you'll get away with it. Okay. Okay. How am I doing for time? Good. Okay. Last little bit. Macroscopic model of an ideal gas. Macroscopic meaning outside, meaning not atoms. So basically, along came Boyle, and Boyle got a syringe and he squished it, measured the pressure, probably using a U-tube manometer, and he figured out that the pressure was proportional to 1 over the volume, as long as he kept temperature constant. So he did it slowly. Then there was about 100 years gap. It's amazing. And then along came Charles, and Charles figured out that the volume is proportional, linearly proportional. So the pressure is inversely proportional to the volume, and the volume is linearly proportional to the temperature, and the temperature has to be an absolute. And in Britain, they say Charles, they don't talk about the third option. In France, they talk about the third option. Gay-Lussac, French guy, did pressure versus temperature, linearly proportional. So this is PV at constant T. This is VT at constant P, and PT at constant V. So 3 experiments. Gap there in time because they didn't know what was going on with temperature.
Is P pressure?
Yeah, P is pressure, T is temperature, V is volume. So you could talk about Boyle's law, and we did that as a lab. You could talk about Charles's law. You could talk about the Gay-Lussac's law. You put them all together, and you say PV over T is equal to a constant.
And temperature is always going to be in Kelvin?
So you say PV over T equals a constant, and you need to be working in SI units or standard units. So you want your pressure to be, well, no, that's not true actually. But you do need to be working in a temperature scale where 0 is 0. And that's why I put down these little K's.
So Kelvin.
You need to be in Kelvin on these things. Okay? So a sample of gas is trapped in a cylinder of a syringe. Initially has a pressure of 3 pascal, so P1 equals 3 pascal. What's room pressure? Room pressure, what's that roughly? Atmospheric pressure in a room.
1.
Pascal?
Oh, in Pascal?
Not 1,000.
It's 101,000.
Yes, 101,000. So this is a really small pressure. Just, and then the volume initial was 4 meters cubed. And the temperature initial equals 127 degrees C. And the gas particles cannot be added or removed, so we can't change the number of gas particles. The chamber volume can be increased or decreased. The sample of gas can be heated or cooled. And show that the sample's volume will be that when the pressure is that. So I'm going to imagine. And now I know the new pressure, the pressure 2 is equal to 10 pascal. So I've increased the pressure. I'm asking for the volume. And the temperature is equal to 327 degrees C. So I say P1 V1 over T1 equals P2 V2 over T2. So 3 times 4 over,
Don't we have to convert to kelvins?
that's what I'm going to do. So we go 127 plus 273 is equal to 10 times V over 327 plus 273. Most common mistake is people will leave it in centigrade. That's 12 over 400, I think, is equal to 10V over 600. So V is equal to 12 times 600 over 10 times 400. V is equal to 7200 over 4,000, which equals something like 9, 8, no, 1, 18, I think. 1.8. I'll get there in the end. 1.8 cubic meters. Cool. What can I do to make this more interesting for you and me?
Can you give us different units?
I wouldn't give you cubic meters, I'd give you cubic centimeters. That would be nice. And I might not give you pascals, I might give you kilopascals. And then if I want it to be really interesting,
Can you give us some in Fahrenheit?
I actually wouldn't do that because I think that's busy work. But yeah, I could.
Is atmospheric pressure?
Use the radius. Yeah, radius is fair game. It's a circle. You know how it works. Yeah, pi r squared. Yeah, syringe. Okay. P1 V1 over T1 equals a constant. But what constant? We can figure that out, and that's actually what we did in Boyle's law, in the Boyle's law lab. we found that PV equals nRT. We figured out what R was. N here is the number of moles of gas. And big N is the number of molecules of gas. And here it's important not to just put down MOL, because you'll have no idea which one you're talking about. So you've got to write out more. KB is Boltzmann's constant. You don't need to know N. Well, you need to be able to calculate N. You don't need to know R. You don't need to know KB. I will give you those. Yes?
What's the difference between moles and molecules?
Oh, so the difference between moles and molecules is that it's like the difference between units and dozens. A mole is a collection of molecules. We can have a mole of people, actually. It's a collection of things. And it's Avogadro's number. Remember that? Yeah. Something like that, yeah.
And molecules is like in actual units?
Molecule is a thing. It's like people. Yeah. So.
What was the little KB stand for?
Boltzmann's constant.
Cool, okay.
So a sample of gas has a pressure of that. So here's our sample of gas. And our P is equal to 4 Pascal. And our V is equal to 7 meters cubed. And our T is equal to 420 K. How many gas molecules? So PV equals nRT. That's not the one I want. PV equals big N KBT. And the way I remember it is, it doesn't take much ink to write a little n, but it takes a lot of ink to write a big N. There's a lot more in a big N than there is in a little n. There's a lot more particles in a gas than there are moles of particles in a gas. So that's my little way. So then I say I want to know what the, how many gas molecules is that? N is equal to PV over KB times T. So N is equal to P for V 7 KB. I gave you KB, 1.4 times 10 to the minus 23 times T. I even gave you it in the right units, 420. So N is equal to, yes?
Will you, on the test, will you tell us what the K?
I'll probably ask you to leave it in terms of KB on
and
the test.
terms of R as well?
No, R I'd probably give you and ask you to calculate, because it's 8. It's like 8.3.
You'll give us that number though?
Yes.
Okay.
Times 7 divided by 420, enter, divided by 1.4 second e to the minus 23 equals 4.7 times 10 to the 21, 4.8 times 10 to 21. Yes. There we have it.